Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to introduce you to electrical power and how it's calculated. So in this example, we're looking at a light bulb, but it really can be any electrical device. It's important to note that no matter what this device is, it's going to have a certain electrical resistance to it. All right, hopefully you've watched my video about electrical current and electrical resistance. And all circuits have at least some electrical resistance. I mean, even a jumper cable has it would be very, very small, but even a jumper cable you can measure a tiny electrical resistance. And the way we would activate this bulb is we would hook it to some sort of battery source. So I want to imagine here that we hook this battery up to this light bulb. Typically anytime we have a circuit we should have a switch involved. Right? So if we hook them up, it might look something like this. Now, when we close the circuit or we close the switch, the battery now is going to drive a current through this circuit. One of the first things we need to realize how to do is draw the circuit diagram for this. So the battery voltage looks like this, right? And again, the long guy represents positive terminal, short guy represents the negative terminal. Sometimes we would include a resistance for the internal resistance of the battery. Sometimes we don't. It depends on how high the currents are, whether it's a good or bad battery. For this example, I'm not going to include the electrical resistance of the battery. I'm just going to get rid of that. It's not relevant for the discussion. Right? In the place of the light bulb, I'm going to put a resistance symbol. So that's what the circuit diagram would look like. Now, some important things about the circuit diagram. This is one of the most important fundamentals that everyone needs to understand, is that this circuit has one loop. Right there. And because it only has one loop, that means it has exactly one current. So there's only one current in this problem. And the current direction, if I draw it, whoops, I'm going to go ahead and draw it in black here. The current would be in that direction, counterclockwise. And the reason is because when we're dealing with currents, the standard sign convention is always assuming positive charge carriers. I usually say that with a smile because in conducting material, the actual charge carriers are electrons moving the other way. But again, the standard sign convention for currents is assuming positive charge carriers. So we'll go ahead and keep assuming that. Now, it's very important to realize something, that current, whatever it is, let's say it's, 2 amps. That means if I take a current measurement here, I'm going to get 2 amps. 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 The current is the same everywhere in that loop. There isn't a changing current in that system. Right? Now, the voltage is the same anywhere we got conducting material. So, again, this is all one potential. But there will be a voltage drop across here because this filament here is going to have a very high resistance. The filaments in a bulb typically are not pure conducting material. And furthermore, this light bulb is really representing any electrical device. And all electrical systems have at least some resistance. So we are going to get a voltage change across this resistor. Now, from experience, everybody knows that, if we touch the light bulb here, most people, and I ask, what do you think you would experience there? Most people would say, ouch. That light bulbs tend to get hot. In fact, all electrical circuits create some form of heat. So there's energy being dissipated here at this bulb constantly. And one of the things we need to be able to do is calculate the rate at which energy is being dissipated across that bulb. And I'm just going to write an expression down. We're going to look at the units. We're going to look at the units of the product of current and voltage. All right, so current times voltage. The current is measured in amps, but an amp in a more fundamental sense is a coulomb per second. Voltage is measured in volts, but remember, electric potential is defined as potential energy per unit charge. So a volt has units of energy over charge, or in other words, joule per coulomb. So the product of the two, you'll notice that these cancel. The product works out to joule per second. And that's an energy transfer rate. That's what we call power. So the power for an electrical circuit, this is how it's calculated, or one of the ways, current times voltage. But that equation can kind of take on other forms. Remember Ohm's law, voltage equals current times resistance. If I wanted to, I could replace this V with the term IR. And if I do that, this is going to read I times IR, which is I squared times R. This is a very common way which power is calculated. A third way I can get from this, I can replace this I, if you look right over here, with V over R. And if I put V over R where that I is, the resulting expression is going to be V squared over R. It kind of looks like a centripetal acceleration. Again, that's not to be confused with centripetal acceleration. That is a voltage, and that is a resistance. So there's really three different ways that power is calculated. Current times voltage, I squared times R, V squared over R. Which one you use, it just kind of depends on the problem. There's a very important fundamental, though, that I want to point out right now. Actually, two important fundamentals. Important fundamental number one. You'll notice that power is very sensitive to current. If I hold resistance constant, but I double the current, there's 4 times the power output. And what that typically means here, as far as electrical circuits is concerned, is a lot of heat loss. As a rule of thumb, it's not very advantageous to run circuits at high currents because there's a lot of heat. Also notice that power is the product of current times voltage. So let's just say, for the sake of example, I want the power to be 100 watts. And keep in mind that's equal to current times voltage. There's in fact an infinite number of combinations that will give me that power. This could be, say, 50 amps times 2 volts. And again, I'm going to put units of amps and volts. But it could also be 25 amps times 4 volts, or 10 amps times 10 volts, or 1 amp times 100 volts. All of these combinations will give me a product of 100 watts. It's very important to realize, though, that as a rule of thumb, high current means high heat, means less efficiency. Heat is the natural enemy to all electrical circuits. So in this example that I have went through, this would be the most efficient circuit. It's always advantageous to transmit power at as high a voltage and lowest current as you possibly can. And I'm going to make more videos talking about why later on. The main points of this video were, one, well, how to draw a simple circuit based on a diagram. 2, the 3 different ways that power is calculated for electrical circuits. And third, at least a quick conceptual understanding that, generally speaking, high current means more heat and a less efficient circuit. So it's much more advantageous to transmit power at low current, high voltage than it is at a high current, low voltage situation. So I hope this video helped at least show you how some of these things are done, kind of in theory. I'll make another video where we go through and do some calculations. Have a great day.